All right. This next theorem, theorem 3, is about the existence of extreme values on a closed interval. So whenever we have a function that is continuous and it's defined on a closed interval, then we know that the function does obtain a minimum and maximum value on that interval. So those are the two things we need: continuous and definition on a closed domain. So using that, let's take a look at example 6 here. We are asked to find the extrema of this function on the interval 0 to 6. So this is definitely a closed interval. The endpoints are included, so that hypothesis is satisfied. And then this function here is a polynomial, and we know that polynomials are continuous and differentiable everywhere. So we know that this function does obtain a minimum and maximum on the interval 0 to 6, and we know that the minimums and maximums occur either at the endpoints of the interval 0 and 6, or they occur at a critical point. So let's just summarize that. So extrema must occur at either the critical points of f within the closed intervals 0 to 6, or at the endpoints of our interval 0 to 6. So, in other words, at 0 or at 6. So, what we're going to do here is first find critical points. So, finding critical points, we'll take the derivative. The derivative is 6x squared minus 30x plus 24. Since the first derivative is continuous, that means the function f is differentiable everywhere, so this always exists. There's no x value that we could plug in here that would make this expression nonsensical. This always exists for any value of x. So the first derivative never doesn't exist, if that makes sense. So because of this, we only need to check when the first derivative is equal to 0. So if we check this, we can then, each of these terms is divisible by 6. So if I divide everything by 6, we are left with x squared minus 5x plus 4. And if we factor this, we should get minus 1, x minus 1 times x minus 4, which implies that x equals 1 and x equals 4 are critical points. Now, one thing we want to make sure we do here is we have to make sure that any critical points we find, that we are only going to care and keep the critical points that live within this domain. So if we were to find somehow that x equals 7 were a critical point of the function f, that's fine, but we're trying to find the extrema here. And since x equals 7 lives outside of this interval, we would just disregard it. But x equals 1 and 4 live safely within this interval, so we're going to keep them. We're not going to just disregard them. Okay? So the next step we want to take here, after we've done this, we want to go ahead and compare. Step 2 is to compare value of f at the critical points and endpoints. So we'll have f of 0 f of 6. F of 0 is going to be 7. F of 6, that is going to be, let's see here. This should be 43. And then f of 1 is 18, and f of 4 is negative 9. So clearly, this right here is the maximum, and negative 9 is the minimum. So there we have it. We have a maximum of 43 that occurs at the right endpoint of our interval, and we have a minimum at x equals 4, which is a critical point of the function. So this is the absolute minimum on this interval for this function, but it does also represent a local minimum. We don't have to make the distinction here because it wants to know the extrema, so we just only have to list what's the biggest value, 43, that's the max, and what's the smallest value, negative 9, that's the minimum. Then we're done.